Alright, if you're watching this video, you're in for a treat. This next section of the course will introduce you to some of Excel's most powerful analytics tools, like data tables, forecast sheets, goal seek, and scenario manager. We'll work on solving complex optimizations with Solver, exploring data tables with cube functions, and even building Monte Carlo simulations using a full-scale roulette simulator. I hope you're excited. Now let's get started. All right, for this pro tip, I want to talk about how we can instantly explore our data using something called quick analysis tools. This is a one-star analytics tip, very simple to use, but a really interesting tool to play with. So most recent versions of Excel, I believe 2013 and onward, include an option called quick analysis tools. And all you need to do is select a range of cells, kind of like this one. You'll see a pop-up appear in the bottom right, looks like a lightning bolt with a bar chart underneath it. And when you click that option or press Control Q, you'll access a quick analysis tool menu. And within this menu, you'll find all sorts of analytics tools, including conditional formats, chart types, calculated rows and columns. You can convert this range to a table. You can add spark lines, all sorts of very, very interesting and powerful analytics tools, all consolidated into this single menu here for quick access. And what that allows us to do is take a raw basic range of cells like you see at the top of the slide and convert it into something like this, either a color scale or adding a calculated column with the average values or inserting a clustered column chart with a click of a button. Anyone who knows me and knows my courses knows that generally speaking, I try to avoid these kind of shortcut tools like this because I guess I'm old school. I like to go through the traditional menus, but I'm actually quite impressed by how smooth and how convenient this quick analysis tool menu is. And as a result, I've started to use it quite a bit more myself. Now, one note here, you won't always see all of these options because those options and those tools may require the data to be in a certain format. So if your selected data isn't compatible with a certain type of tool like a sparkline or a pivot, for instance, you may not see that option in your quick analysis toolbar. So most common use cases here, obviously just quickly exploring a variety of popular data analysis tools without having to manually navigate through different ribbon options. And also I've found it's a great way to quickly add calculated rows or columns for things like sums, counts, averages, totals, without having to actually type in a single formula. So let's jump into Excel. We've got a good range of data that we can use to practice some of these quick analysis tools. All right, so if you'd like to follow along, go ahead and open up your pro tip workbook, head to your table of contents, and we're going to scroll all the way to the right to our analytics tips. And in this case, we want the quick analysis tools demo. Go ahead and link straight out to that sheet. And what you'll see is a simple range of cells here. We're looking at movie IMDb scores, averaged out by year, 2011 through 2015, and by genre here in column A. Now, this is a great sample bit of data to use to practice these quick analysis tools because it's two-dimensional. We've got a nice range or table of values here that we can use for value-based conditional formatting, things like color scales and icon sets. We've got time series or trending here with 5 years of data, so that we can show things like running totals or line or column charts. We've got opportunities to add calculated rows in row 13 or calculated column or spark lines here in column G. So it's a good versatile data set to really see a wide range of options for these tools. So let's go ahead and select A2 all the way down to F12. Note that I'm including the headers as well. And as you can see, if you hover over that range that you've selected, you'll get that quick analysis pop-up right here in the lower right. Go ahead and click or press Control Q, and here we are in the quick analysis menu. And you've got formatting options, chart options, totals, which are calculated rows and columns. You can add tables or pivots, spark lines. So all of really the most popular and powerful analytics tools packed here into a single convenient menu. Now, perhaps my favorite feature is the fact that you don't even have to commit to any option in order to see the output. So you get this kind of quick preview in your selection as you simply hover over these different options. And if you'd like to make customizations, which is something that I often do like to do, as you click through these tools, you'll actually access the formatting dialog box where you can customize, exactly what you want here, and then press OK. And just like any other change, press Ctrl Z to undo, and you can jump right back into those tools. So the formatting options, really speak for themselves. Very simple. For charts, basically this just inserts a new chart as a workbook object. Got different common options here at the front of our list. In the total section, we can add calculated rows, which are shown as this kind of blue shaded row here in the icon. Or if we continue to the right, we can add calculated columns. And this uses your most popular aggregation or summarization modes: a sum, an average, a count, a percent of total, and a running total. And again, very easy to add without typing a single formula there. We can convert our range to a table, insert a blank pivot table straight from here, or we can add spark lines. And Excel knows right off the bat that the most appropriate place to drop spark lines in this case would be right there in column G. So again, I've been very, very impressed by these tools and by how smooth and convenient they really are. So I'd encourage you to either work with the data shown here or drop in a sample of your own and just explore how these quick analysis tools can help you analyze and understand your data. All right, let's take a few minutes and talk about Excel's Scenario Manager tool, and specifically how this tool can be used to quickly compare different model outputs. So the Scenario Manager, which you'll find in your Data tab under the What If Analysis options, essentially allows you to save and quickly access specific combinations of preset cell values. So let me show you an example here. If we drill into that Scenario Manager option, we'll see a list of any predefined scenarios that we've created. In this case, I have 4. And what happens when you add or create a new scenario from scratch, you're basically telling Excel, I want to define a scenario based on this specific set of cells. In this case, I have 3 of them. I've named one cell percent down. I've named a second cell interest rate and a third cell term length. Now, a quick tip here, you don't have to give your cells names. This could just say H7, H8, H9. I find that naming those cells helps make this process a bit more intuitive and user-friendly. So essentially, we're telling Excel that we're defining a scenario based on particular values for each of these 3 cells. In this case, I've named the scenario 20% 30 years. And for that scenario, I want cell 1 to change to a value of 0.2, 20%. I want cell 2, the interest rate, to change to a value of 0.0475 or 4.75%. And I want to change cell 3, the term length, to 30. Now, once you've defined and named that scenario, you can quickly view it and automatically change those cells to the values that you've configured. Now, this is very often used for modeling exercises, which allow you to fix different combinations of inputs, like these 3 cells here, the down payment, the interest rate, and the term length, in order to calculate the effect on a certain formula-driven output, in this case, the cash to close on the property and the estimated monthly expenses. And if we were to continue this process and create 3 additional scenarios, then with a click of a button, we can quickly compare 4 different outputs based on those 4 combinations of our inputs. So as you can see, great tool for quickly evaluating the impact of different combinations of input values. Now, common use cases, this is often used for building forecasts that are based on several variables that may change, like seasonality, interest rate, etc., or modeling several potential outcomes in cases where uncertainty or risk is a factor. For instance, creating a scenario for low risk, medium risk, or high risk to predict your stock portfolio returns. So with that, let's jump into Excel and create some of these scenarios for ourselves. All right, so go ahead and open up your Pro Tip workbook. If you're following along, head to Scenario Manager in the purple Analytics Tip section, and let's go ahead and link straight out. Here we've got a property cost calculator. Now, for those of you who've been following along with the entire course, this may look familiar from our formula auditing tip, but basically we're evaluating 2 key numbers here: the cash required to close on the property and the estimated monthly expenses, both of which are determined by a number of factors here in columns G and H. Purchase price of the property, the tax rate, different loan conditions here, which we're going to be focusing on in this demo, as well as other factors like utilities, insurance costs, fees, and so on. Now, you'll notice that I've named each of these cells using the name box right here to the left of the formula bar. So percent down, interest rate, and term length. And again, that just will make it a bit more readable, a bit more intuitive once we start creating some scenarios. Now, the idea here is to essentially preset a number of combinations for these three values in H7 through H9 in order to quickly and easily determine the impact to our key outputs here. And there are a few ways to do that. We could turn these into data validation drop-down cells, containing a limited list of options and have users manually select those combinations. But in this case, we really have 3 or 4 combinations that are most likely and most realistic. And to kind of preset those combinations, the scenario manager will be a great tool to use in this particular case. So let's go ahead and select the 3 cells that will be part of our scenario, H7, H8, H9. We're going to go into our Data tab, drill into the What If analysis tools in our Forecast section, and click Scenario Manager. So from here, we're going to define 4 different scenarios for the purpose of demonstration. The first will be 20% down at a 5% interest rate for 30 years. So let's go ahead and add this one. Now you can give it whatever name you want. In this case, I'm not going to be very clever. I'm just going to actually type in what we're using for our inputs. So 20%, 5%, 30. And since we've selected H7 through H9, Excel already knows that these are the 3 cells that we'll be changing to define this scenario. And then you can add comments here, customize the protection. In this case, we're preventing users from making changes, and press OK. So here we go. It's populated with the current values in those cells, and we can just modify them to fit our criteria. So percent down is 0.2. Whatever's easier for you. You can type 0.2 or you can actually type 20% here. I kind of like that approach a bit better. It's a bit more readable. Interest rate in this case is 5% and the term length is 30. So press OK there, and it's created our scenario. And now watch what happens when I click this Show button. Boom, it's changed that interest rate to 5%. So now those 3 cells take on the exact values defined by that first scenario we just created. So same process, let's cruise through and add 3 more. The second one's going to be 20% down at 4% over 15 years. So 20%, 4%, 15. Press OK. 20%, 4%, 15 years. All right, let's continue on. This next one's going to be a lower down payment, so only 10% down at 5% over 30 years. And I know I'm moving quickly, so feel free to slow things down to follow along. But here we've got 10, got 5%, that was correct, over 30 years, that looks good. And finally, we'll add our 4th here, which is 10% at a 4% interest rate over 15, and press OK. 10%, 4%, 15. There we go. So now we've got our 4 scenarios defined here. And to quickly determine the impact of each of those scenarios on our output cells, all we need to do is select the scenario and click Show. So now check that out. It changed to 20%, 4%, 15. Click the third item, click Show, 10%, 5%, 30, and then the last option, 10%, 4%, 15. And every time we change these items, you can see that our cash to close and or our monthly expense calculation change accordingly. So there you go. Quick demo of using the scenario manager to define preset combinations of cell input values. All right, this next pro tip is a fun one. We're going to talk about how to solve for individual outputs or simple optimization models using Excel's Goal Seek tool. Now, Goal Seek, which you'll find in your Data tab under the What If analysis options, basically allows you to find the result that you want by allowing Excel to automatically change the value of a single given input cell. Goal Seek requires very simple inputs and outputs. You need to determine a single hard-coded input cell and a single formula-based output cell. We can't add other conditions here. We can't test combinations of multiple inputs. For those more complex optimization problems, we'll be using Excel's solver tool in a more advanced demo in the course. So consider a case like this. We have a value-based input, which is the quantity of units sold right there in cell C2. We have a set of calculation factors like the unit price or retail price, the cost to produce each unit, and a certain flat fixed cost. And with those factors, along with the quantity value, we can determine the profit, which is our formula-based output. In this case, our profit will equal the quantity times the difference between the price and unit cost minus the flat fixed cost. So this particular scenario, this simple model, checks all the boxes for the goal-seek tool. We've got a single hard-coded input, quantity, and a single formula-based output, the profit. So let's see what this actually looks like. When we drill into that goal-seek tool, you'll see a dialog box that looks like this. And what we're doing here is we're setting our output cell, C8, which is our profit, to a specific goal or target value, in this case $1,000, by changing that value-based input, C2, the quantity. So in plain English, we're telling Excel, I want you to change cell C2 however you need to in order to land at $1,000 of profit. How much quantity or how many units do I need to sell to make $1,000? And when you configure goal-seek this way and press OK, it automatically produces these values. You've fixed your profit to $1,000, and kind of working backwards to the quantity, that equates to 833 units sold. Now, common use cases here, just like we're showing here, determining the ideal input required to produce a specific goal or target outcome. For instance, we could do a profit of $1,000 here. We could do a profit of 0 in order to figure out how much quantity we need to sell to break even, any combination like that, or really just solving any simple optimization problems that are based on a single input variable. So let's bring this example into Excel and practice configuring the goal-seek tool ourselves. All right, so if you'd like to follow along with me, open up your pro tip workbook, and from our table of contents, we're going to drill into our goal-seek demo in our analytics tips section, and go ahead and link out. And here you'll see our familiar, very simple model based on this one input, quantity, and this one output, the profit. And as you can see, if I select cell C2, this is simply a hard-coded value. We've got some predefined calculation factors here for the unit price, the unit cost, and the fixed cost. In our profit cell, C8, this is our formula-driven output, which takes the quantity, multiplies it by the unit price minus the unit cost, and then subtracts out the fixed cost at the end to determine the actual profit. So as you can see, you can adjust different values here. Say, okay, if I sold 325 units, my profit would be 238. If I sold 23,000 units, my profit would be 34,250, and so on and so forth. So the way a lot of users who aren't familiar with goal-seek will use Excel, and specifically use a model like this, is, let's say we want $10,000 of profit. You might say, okay, let's try selling 8,000. Well, that's too many. Let's try 7,500. We're still too high. Maybe 6,000, too low. 65. And you're kind of trying to narrow in on that number using the guess and check approach. And this is exactly what goal-seek is designed to automate for you. And while you also can kind of back into the formula to create that optimal quantity value by presetting your profit, goal-seek is designed to do that for you, go through that process, and not make you kind of reverse the calculations to figure out that number in C2. So let's jump into our data tab. We're going to look at our what if analysis tools and click on goal-seek, our second option here. And all we have are 3 conditions here. We're going to set a specific cell, which is our profit. We're going to set that profit to a specific value, and this could be anything. Let's actually start with $0. I want to find the break-even point, and we want to do that by changing a given cell, which is the quantity here in C2. And all we need to do is press OK. And check it out. It just automated the process of solving this for us. So target value was 0. It optimized, it found current value of 0. Press OK. And this tells us that, okay, we need to sell 167 units before we break a profit. And to kind of confirm this, if we choose 166, well, we lost $1. If we choose 168, we made $2. And you can very quickly test different scenarios here. Like in this case, we want to set the profit to 100,000, for instance. Same exact process, same exact inputs. Press OK. And there you go. Found a solution and told us that, okay, for a $100,000 profit, you've got to sell 66,833 units. So there's your crash course in GoalSeek. It's a pretty amazing tool when you need to optimize simple single input and single output models in Excel. All right, time to talk about one of my favorite analytics techniques, forecasting. And specifically, I want to show you how we can create forecast sheets using historical data in Excel. Now, recent versions of Excel, I believe starting with 2016 and Office 365, include a built-in forecast sheet tool that allows you to calculate forecasts based on a given set of historical values. So for instance, if we have basic data like this, monthly average temperatures, which in this case actually continue to extend through about 6 years worth of data, what we can do is select both of those columns, including the month or the date indicator, as well as the values, drill into the Data tab, and click on the Forecast Sheet tool right next to the What If Analysis options. And when we do that, we'll see a basic preview of the default forecast that Excel has produced, as well as options to customize things like the forecast length, the confidence interval, any seasonality, and also customize how to handle things like missing or duplicate values. And once you've configured those settings as you'd like, Excel will produce a sheet that looks something like this. This is the actual forecast sheet. It's a new tab in your workbook, and it contains the seasonality chart, as well as a new table of data containing your existing historical values, as well as a set of calculated forecasted values. And I'm going to show you a couple examples of exactly what this looks like in Excel. Now, one quick note, sometimes you can use tools like trend lines for very simple forecast exercises, but keep in mind that those won't account for things like confidence or seasonality. So for more complex or custom cases, I definitely recommend using this forecast sheet option instead. So common use cases here, for one, predicting any future values such as interest rates or stock returns. And two, if you want to calculate an expected range of future outcomes based on a given level of confidence, this forecast sheet and the formulas that it produces are very, very helpful for doing that. So with that, enough talk. Let's go into Excel and practice building our own forecasts. All right, so for those of you following along with me, head to your Pro Tip workbook. We're looking for the basic forecasting demo in our purple analytics tips section. Go ahead and link straight out. And here you'll see two different sets of data. We've got stock market data here in columns A through E. We're looking at Apple stock prices, the closing price and the volume by day. And we also have some monthly average temperatures from Barcelona, Spain, which span about 6 years worth of data. So two very, very different types of data sets that we're going to use to practice forecasting. So let's start with our stock market data here. And one thing I want to show you is if we were to select column B and control click the values that we want to forecast, which in this case will be the closing stock price. Now if we go to our data sheet and choose forecast sheet next to what if analysis, you'll see this error message. It says, hey, we can't create a forecast because your timeline isn't evenly spaced. In other words, you've got inconsistent gaps between some of these points. And the reason that's the case is because the market is closed on holidays and weekends. So we have these gaps, like March 2nd and 3rd, where we don't provide any data here. There's no closing price or volume. So what I've done is add a new column here, column C. That's just a series of sequential values or an index that basically just labels the days, day 1, day 2, day 3, regardless of whether it's a weekend or a weekday or holiday, whatever it might be. And now if we select column C and D and go back into our forecast sheet, now we're able to produce an actual forecast. So Excel will take its best guess at your settings, your forecast start, your forecast end, your confidence interval, seasonality, etc. But if you want to customize exactly how this is configured, go ahead and drill into the options in the lower left. And here we've got a bunch of additional options to choose from. And one option is to change how far out you want to forecast. So maybe instead of 1,574 days, maybe we only need to forecast to 1,400 days, which kind of shrinks the forecast length a bit. Another option is to actually change when the forecast begins. So by default, this forecast is going to begin on the last day that we have actual values. And the reason why Excel defaults to taking that approach is that allows it to kind of use all of these data points, all of these historical actuals to help generate the prediction. But what we can do is change this, to something like 1,000 days and force Excel to start the forecast earlier. And basically it gives us a period of overlap where we can actually compare the forecasted values to the actuals. Now, the downside, which we're seeing the result of here, is that by doing that, by accelerating the forecast start, we're feeding less historical information to Excel and therefore potentially impacting the accuracy of the forecast itself. So maybe we kind of split the difference here and say start at 1,100 days. That looks pretty good. We still have a good chunk of overlap here, but that seems to be a slightly more realistic forecast. Now, the other items that we can customize here are the confidence interval, and that's basically creating these two bounds, the upper and lower bounds, and telling us that we can be 95% confident that the actual observed values in the future will fall within these bounds. So watch what happens when we increase the confidence to 99. You'll notice that the bounds get further apart. We're creating a wider window that could potentially contain our actual future values. And if we shrink this down to something like 50% confident, now we have a much narrower bound and a much more difficult target to hit. Therefore, we're less confident that the actual values will always fall within this range. So generally speaking, you're going to want to stick with something like 90 or 95. Those are kind of standard. And from here, we can also deal with seasonality. By default, Excel will detect seasonality automatically. In this case, if there were a certain number of days or a certain period where we see a pattern repeat over and over and over, we could set that pattern manually. And I'll show you exactly how we could do that for the weather data. And then when we create this sheet, we can also include some forecast stats if you'd like. Just check that box. And last but not least, we've got our timeline range in column C, our day index. Values live in column D. And then we can choose if we had missing points, we could interpolate or leave those as 0. In this case, we don't have any missing points. And if we happen to have duplicates, we could choose how to summarize or aggregate those duplicates. In most cases, average is an appropriate choice there. So with that, I'm confident, I'm happy with our choices, the way we've configured this. Let's go ahead and click Create. And what Excel does is insert a brand new sheet here. It gives us a little pop-up to welcome us to our new sheet. And it says, great, we've created a table with a copy of our data, columns A and B, along with the forecasted values and our confidence bounds in columns C, D, and E. So got it, sounds good. Let's go ahead and drag this sheet to the right of our forecasting sheet and name it something like Stock Forecast. Check it out, it's included the chart for us just like we previewed. It's included these forecast statistics here in this little mini table in columns G and H. I won't get into those right now. And then got our actual copies of our historical data points here in columns A and B. And if we scroll down, or even more efficient, select an empty cell and use the control arrow down approach. Here we go, the last day of our observed values, or in this case, the first day that we determined that we want our forecast to start. Now these new columns are being populated here as well. And they're actually being populated with forecast formulas that are feeding in inputs based on how we configured our settings in the dialog box. And same thing with our lower and upper confidence bounds. We're using confint or confidence interval formulas here. So if we wanted to tweak any of these settings, we could either go back and create a brand new forecast from scratch using the dialog box, or we could go ahead and update individual inputs or arguments of these functions and have the table update dynamically. So really helpful tool there. Let's scroll to the top. And one thing I want to show you here is that in this case, we can edit this chart just like any other. And let's say that we wanted to follow a simpler approach for forecasting these stock values and simply go to our chart tools, add a chart element, and throw a linear trend line in place. So that created this blue dotted trend line, which, as you can see, follows almost the exact forecast that Excel has created. So in this particular case, using a linear forecast as a very quick, simple first pass might be a valid approach. And in fact, it's going to produce almost exactly the same values as our forecast here. But that's not always going to work. And one case where it often falls short is a case where you have seasonality. So let's jump back to our basic forecasting sheet, select columns G and H this time, which is our monthly temperature data, go back into data, and let's see what happens here when we choose forecast sheet. So take a look at this. Very, very different pattern here. And there's clearly seasonality that's happening over the course of those 6 years of actual values. So the difference between this example and the stock example is that A, we can't just slap a basic trend line option here to follow this forecast path because there is a seasonality trend happening because literally we're looking at seasons worth of data. So Excel is saying, all right, we've detected seasonality automatically. And if you set it manually, we're basically saying every 12 points, which are months, we see the same pattern repeat, which makes sense. So in this case, I won't create a new sheet because it'll look just the same as the other one. But there you have it, 2 good examples of how to use Excel's forecast sheet to provide predicted or forecasted values using 2 very different types of data. All right, for this pro tip, we're getting a little bit more advanced. This is a 4-star analytics tip. We're going to talk about how to find or detect outliers using a combination of stats functions and conditional formatting. Now, what we're going to do here is use functions like median and quartile to actually calculate statistical outliers, and then we're going to apply conditional formatting rules to draw attention to them or highlight them within our columns. So in this case, we're looking at athlete data with names in column A, we've got heights in column B, and weights in column C. And what we'll be doing is creating the outlier calculations using those stats functions. We'll calculate the median value, the first quartile, the third quartile, the interquartile range, or IQR, and something called the fence multiplier. And that fence is essentially what determines how far out of the norm a value must fall in order to be labeled as an outlier. And what we'll end up with is a range of values defined by the inner or lower fence and the upper or outer fence, meaning that any values that fall outside of that range will technically be labeled as an outlier. So from there, all we need to do is head to our Home tab, Conditional Formatting Rules, and we're going to use a custom highlight rule to highlight cells that are not between those fence values in cells F8 and F11. And when we apply that formatting rule to, in this case, column B, immediately we see those outlier values highlighted in yellow. Now, one thing to note, if you're dealing with much simpler calculations or formatting rules, like the top n values or a specific top percentage, just use basic conditional formats. You don't have to go through this entire process, but what we're doing is using actual statistical functions to define those outliers in a little bit more of a scientific way. And as I'll show you from here, we can kind of adjust our fence and see how that impacts which cells are being highlighted and labeled as outliers. So common use cases here, first and foremost, identifying any statistical anomalies in a data set based on this custom criteria that you define. And second, finding and removing values that may have been incorrectly entered. So if we saw a height here of 800 inches, that will very quickly be flagged as an outlier no matter what settings we choose. And that would be a pretty good indication of user input error and not just a very, very tall human being. So with that, let's jump into our pro tip workbook. We're going to take a look at this exact demo data set and run through this process step by step. All right, so if you're following along, you should know the drill by now. Head to your table of contents and look for the Outlier Detection demo in our purple Analytics tip section. Go ahead and link straight out to that sheet. And what you'll find here are the player names or athletes in column A, and just like we described, heights and weights in columns B and C. Now our goal is to populate these statistical calculations here in column F to determine exactly how we're treating and defining outliers. So we're going to start with median in cell F2. This won't actually be used in our outlier calculation, but it's a great summary stat to include. So I'm just going to use the median function, point to column B, press OK. That tells me that the median height in this sample is 74 inches. Now that brings us to the quartile functions. I'm going to start by typing a quartile formula. And what you'll see are three different options here. You've got the EXC or exclusive version, the INC inclusive version, and the original quartile version, which is a compatibility function compatible with earlier versions of Excel. And what this tells you is that originally there was just the quartile function, and then starting in, I believe, 2010, Microsoft started introducing new variations of that formula. Now, in this particular case, we'll see the same answer no matter which version we use, but I want to show you the INC, the inclusive version right now, so I'm going to tab that in. All three versions use the same arguments, starting with the array, column B, and then the quartile, which you can label with a 0, 1, 2, 3, or 4. And in this case, we want the first quartile, or the 25th percentile. I'm going to press a 1 there and close it off, and press enter. Now, what this tells us is that players who are 72 inches tall are at least as tall as 25% of the other rows or players in the sample. Now, a little bit of a nuance here, but the difference between the inclusive and exclusive versions is that the exclusive version would basically determine the value that's greater than 25% of values in the array. The inclusive version determines the value that's greater than or equal to 25% of values in the array. So that's the difference there. That's the nuance. Exclusive acts like greater than, inclusive acts like greater than or equal to. And one other note here, if you did want to use this function to return the minimum or maximum value with a label of 0 or 4, you would have to use the inclusive version to do that. So let's go ahead and drop our 1 back in there, press enter. We can simply copy that formula, paste it here for a third quartile, simply change the 1 to a 3, and we get a 75. Now IQR is our interquartile range. That's as simple as the third quartile in F4 minus the first quartile in F3, which is a 3-inch range. And next up, our fence multiplier. Now what the fence does is essentially determine how far outside of our interquartile range a value must fall in order to be labeled as a statistical outlier. So the higher the fence, or the higher the fence multiplier, the further from our expected range that value needs to fall to be considered an outlier. And this is a hard-coded value. In many cases, 1.5 is kind of a good standard starting point. So let's go ahead and start there. And then last but not least, we need to determine our inner fence or lower fence, as well as our outer fence or upper fence. So the lower fence is defined as the first quartile minus, open parenthesis, interquartile range times our fence. So F3 minus F5 times F6. That returns a 67.5. That means that the lowest value a cell can take before it's treated as an outlier is 67.5 inches. Very similar logic here for the outer fence or upper fence. We're going to take the third quartile and we're going to add the IQR times the fence multiplier. Close it off, press enter. Same thought process here. The highest value a cell can take before it's treated as an outlier is 79.5 inches. Now from here we've done the hard part. The last step is to actually flag or draw attention to the actual outliers that we've defined here in column B. So let's grab B2, hold Control, Shift, arrow down to grab the entire column. We're going to go into our home menu, conditional formatting, and we're going to use some highlight cell rules here. And what we really want is cells that have a value that's not within the range of our upper and lower fences. So we want a not between option here. which we don't have as one of our standards. But if we go into more rules, here we have that option where we can say format cell values that are not between, and then we can simply point to the cells that we care about, which are all the way up here at the top. So we want to highlight cells that don't fall in this range, so they're not between F8 or F11. And we can apply format. This one's up to you. I'm going to use kind of a yellow fill here and press OK. And check it out. When we press OK, now any value that's higher than the upper fence, greater than 79.5, are now highlighted. And if we jump to the bottom, control arrow down, we've got two values here that were below the lower fence of 67.5. So we've essentially flagged those outliers based on our statistical conditions or a configuration here. And now watch what happens if we change this fence multiplier from a 1.5 to a 1. Now we're including more values that we're labeling as outliers here because we've created essentially a narrower range of normal values. If we change this fence multiplier to 2 or expand that fence, now we're making it less likely that a value is labeled as an outlier. So we only see a few data points here in column B that get flagged. In this case, 3 of the tallest baseball players in the game. So there you have it. Great little crash course on how to use some of these relatively simple stats functions combined with conditional formatting to actually detect and flag outliers in your data. All right, for this pro tip, we're going to talk about a 4-star, relatively advanced analytics tip, and we're going to discuss how to evaluate variable inputs using Excel's data tables. Now, the data tables that we're talking about here are different from your standard cell ranges formatted as tables. In fact, I wish Excel gave them a different name because they actually operate quite differently. What we're talking about are the data tables that you'll find in your data tab from the what if analysis tools. And what these data tables do is they allow you to calculate an array of results with the click of a button based on an entire range or variety of potential input values. So to show you what I mean by that, we're going to look at our property cost calculator tool, which we've seen before throughout the course. And the idea here is to understand exactly what our mortgage cost or our monthly mortgage cost would look like based on different interest rates, ranging all the way down from 3% up to 10% in half percentage increments. So the manual, kind of tedious old school approach would be to plug in those different interest rates into cell H8 and see what the mortgage costs spit out in cell H14. But instead of doing that, we're going to get a little bit more sophisticated, and we're going to select this table, this blank range in columns J and K, and we're going to use Excel's data table tool to produce an array of results based on that range of interest rates. So we're going to head to our data tab. We're going to drill into the data table option from the what if analysis tools. And then here we only have two potential inputs, a row input cell and a column input cell. And in this particular demo, all we have is a column containing that range of values, and the cell in which we want to test that range of values lives in H8. So by treating H8 as the column input, Excel is able to spit out this entire array of results right there in column K based on the range of interest rates in column J. So rather than manually testing 15 or so different interest rate values and recording the results, or typing a formula 15 times, we've configured the data table tool one time and produced all of the results with the click of a button. Now, data tables can be used to evaluate results like we see here based on changes to either a single input variable, like we've shown with interest rate, or with multiple variables, in which case we'd also plug in a row input cell. And I'm going to show you an example of both as soon as we jump into Excel. But real quick, common use cases, calculating a matrix of results based on combinations of input values, like this, monthly payments based on things like interest rates and down payment amounts. Or taking that even a step further, you could use this tool to identify the optimal outcome given multiple combinations of variable inputs. So let's go ahead, open up our pro tip workbook, roll up our sleeves, and practice building some of these data tables. All right, so from your table of contents, go ahead and scroll over to the analytics tips. We're going to look at the data table demo in this case. Go ahead and link straight out to that purple tab. And here you'll see our property cost calculator, which, as we've seen before, takes a bunch of inputs like the purchase price, the tax rate, and some loan terms, and spits out outputs like the loan amount, the mortgage costs, property tax, etc. Now, what we care about in this case is the monthly mortgage cost here in cell H14. And this mortgage cost is a function of a few different factors. For one, the down payment, and for two, the interest rate, among others. So if we change our down payment from 20% to 30%, you'll notice that our monthly mortgage costs are reduced. By contrast, if we change our interest rate from 4% to 5%, our mortgage costs increase. So these two factors both impact the mortgage cost. So what we're going to do here is create two different data tables to test or evaluate different combinations of those potential input values. So in our first case here, all we're testing are variations in the interest rate. So step one is to create a column containing each of the variations in the interest rate that we want to test in order to see the impact on our output formula or our mortgage costs. And I've just got to show you this tip here. You can either type in these values manually, or what you can do, I'm going to delete those. You can type your first value here, hover over the lower right corner, and listen to this. Hold the right click button, drag down and back up, then release to access this kind of hidden menu here. And what we're going to do is drop into series at the bottom. We're going to fill a series in a column, and we're going to step or increment by 0.5%, and we're going to stop at 10%. That's our max value. Press OK. Boom, it's filled that perfect incremental series for us with one click of the button. Now, the goal here is to populate these blank cells here from K4 through K18. And in order to do that with data tables, we have to set things up in a very specific way. Step one, which we just achieved, is laying out the range of input values. Step two is actually linking to the formula that we're looking to evaluate. So we're just taking the formula from H14 and we're referencing it right here in cell K3. And what that's going to allow us to do is select this entire range of cells, which includes both the formula itself and the variety of input values. And from here, we can go into our data tab, what if analysis, data table. And again, just like our demo, we don't have any input variables in a row, but we do have variable inputs in a column. And the input cell itself is not this range that I just created. It's the cell that's actually referenced in the formula that contains the interest rate, which in this case is cell H8. And that's all we need to configure this data table. Press OK, and there we go. It's populated all of the monthly cost outputs based on this different range of interest rates. And as you can see, it's generated a single array or table array rather than 15 individual formulas here. So moving on to our next demo, we're going to follow that same approach, except we're adding one additional set of criteria here for different down payments. So what we'll do here is create an actual matrix of values that account for not only changes to interest rate, but also changes to down payment, either 5, 10, or 20%. So very similar process here. I'm going to select the entire range of cells, including the formula and the variable row and column input cells. We're going to go into data, what if analysis, data table. And now we do have a row input cell, and that's the cell in the formula containing our row input variations, which are the down payments. So our down payments live in cell H7. There we go. And again, our column is the cell containing the interest rate, which is our column index. And press OK. And there you have it. We've produced a single two-dimensional array this time that produces output values based on multiple criteria. So there you go. These data tables in Excel can be a little bit tricky, a little awkward to work with at first, but once you really get a handle on them, they can be a great tool for evaluating an entire array of results based on variable inputs. All right, I want to take a few minutes and walk you through a quick and brief introduction to one of the most powerful tools in Excel called Power Query. Now, this is a 4-star advanced analytics tip. We're going to talk about how to connect, shape, transform, and load data from external sources into Excel using these Power Query tools. So, in classic Microsoft fashion, you may see these tools named all sorts of different things depending on the version of Excel that you're using. You might see Power Query, you might see Get Data, you may see Get and Transform, and it all means the same thing. I'm using Office 365 Pro Plus, and this is what I see in my Data tab. I've got a group of tools called Get and Transform Data, and a Get Data command off to the left. And what we're going to do in this demo is connect to a flat CSV file. Note that you can also connect to database sources or web APIs and so on and so forth. In this case, we're going to keep it simple. I've made this file available as part of the course. Basically, we're going to do a quick analysis of some Kickstarter campaign data. So once we point to the file, we'll see this query preview and then click Edit to launch our query editor. And this will open as a separate workbook outside of our Excel worksheet environment. And you'll see a preview of your data here and all sorts of tools that we have to shape and filter and customize and transform this data before we load it into Excel. So this is like our command center for configuring this query or connection. Now keep in mind there's no way I could even scratch the surface of all these tools within the scope of this particular demo, but I do have an entire course that goes in depth into these tools. It's the Power Query, Power Pivot, and DAX course. Now, for the purposes of this introduction, keep in mind that there are a few important sections of this query editing window. You've got your query editing toolbar at the top with options to transform or add new columns, and a window in the lower right called Applied Steps. Now, these applied steps are absolute game changers because essentially what's going on here is that every time you make an adjustment or transformation, any operation that you apply to your table gets recorded as a new applied steps, exactly like steps get recorded in a VBA macro. Now, once you've transformed and shaped your data and you're ready to load it into Excel, there are two places where you can load it, either to a worksheet where it will live in rows and columns and cells, or to the data model where you can compress this data and store much more information, hundreds of millions of rows. And it's also where you can actually build relational models to create table relationships and connect or blend information from multiple sources. So to quickly summarize common use cases, number one, connecting to flat files or database sources, and then transforming or filtering that data before loading it into Excel for further analysis. Number two, creating a fully automated ETL process, which stands for extract, transform, and load, that can be refreshed with one click as new data becomes available. Again, details are all covered in my Power Query, Power Pivot, and DAX course. So with that, let's jump into Excel. I'm going to walk you through one quick demo for how we can use Power Query to connect and transform an external CSV file. All right, so if you'd like to follow along, head to your table of contents and look for this Power Query demo in our purple analytics tips. And when you link out, all you'll see here is a blank sheet for now. Now, to introduce this topic of Power Query, I've made a project file available to you called kickstarterprojects.csv. Feel free to download that to follow along, or just sit back and watch the show. So I'm going to head to my Data tab here. A couple ways I can grab a CSV file, either from this From Text/CSV button, or in the Get Data dropdown, which shows me some of the other data sources as well. In this case, I'm going to go into From File, From Text/CSV. I'm going to double click the Kickstarter project file that I've loaded to my desktop. So the first thing we'll see is a quick preview based on the first 200 rows of that file. Got project IDs, names, categories, main categories, and then all sorts of information about when the project was launched, when the deadline is, how many backers, how much money was pledged, and so on and so forth. Now, we're going to want to filter down this data, trim it down to just what we need, so we're going to click the Edit button to actually launch the query editor. And you'll see that it launches in a new window outside of the Excel spreadsheet environment. And this is where we're going to do all of that data shaping and filtering and transforming before it gets loaded into Excel. And you'll notice it's already applied a few steps. It's identified the source from my desktop here. It's promoted the headers, and it's detected some of the data types here and applied those data types automatically. So for the sake of demonstration, let's add a few more filters here. Perhaps we don't want all of the deadline data here. We've got projects going back to 2009. So let's apply a date filter and say only projects, get out of here, Adobe Reader, that are after, why don't we say 2014. So we can go to December 2014, select the 31st, press OK. We've added a new applied step to filter those rows, and we can sort that column ascending just like we would with any Excel table to see that now we're dealing with projects that only have deadlines going back to January 1st, 2015. Now, same story here. We can filter down by country. For now, let's just look at the US projects. There we go. And now the state, whether a campaign was successful or if it failed or was canceled. Let's apply a filter there as well and only look at successful projects. Press OK. Now we could continue to go on and on. We could change data types here. We could remove extra columns. We've got some redundant ones in this case. But for the sake of demonstration, let's go ahead and move on to loading the data. I'm going to choose Close and Load To from the upper left. And this will show me my loading options. Now, if I didn't want to load this data to a worksheet and actually store those rows, those observations, in rows and columns, what I could do is only create the connection and drop it into the data model. Now, note, you may not have access to the data model depending on the version of Excel that you're using. And in this case, I want to reserve the data model conversation for a different pro tip. So for now, we're going to use the table option and actually load this filtered data that we created right here into our existing worksheet, the Power Query worksheet, in cell A1. And when we press OK, we'll see our query pane pop up, and it says, all right, we're loading some data from that Kickstarter project CSV. It loaded 41,097 rows, and it dropped that data as a table right here in my Power Query tab. Now let's go ahead and close that pane. From here, we can work with this table just like any other. We can insert a pivot table, for instance. Let's drop this in a new sheet and tab over. And we can call this one Kickstarter Pivot, for instance. And here we've got our fields from that Kickstarter table. And we can work just like a normal pivot table here. Maybe we want to break down data by main category here on rows. And in this case, let's look at the amount pledged in US dollars. And just like any other pivot, we can change the number formats to currency. Could have done this in the query editor as well. And let's grab the state, the project state, as filters. And remember, we sorted it or filtered it down to only show successful projects. So that's the only option we have here. Now that's pretty cool. We can now see how much money was pledged by category. See a lot of money in design, in games, in technology, which makes sense. But this isn't really what makes Power Query so powerful. We could have just loaded up that CSV and copied and pasted it into a tab. What makes Power Query so powerful is that if we now want to change some of the settings or features of our connection, maybe we don't want to filter down to only successful projects. Maybe we want to look at failed projects now instead. We don't have to reinvent the wheel. We don't have to manually filter down the table that was dropped into our Power Query tab. Instead, we can go into Data, Queries and Connections, and we can right-click to edit that Kickstarter project query. And check it out. This last step, this filtered row step, is where we had filtered down to country equals US and the project state equal to successful. All we need to do is click this little gear icon to edit that step. And this second line here is the state filter. Click this ellipse, delete that filter, and press OK. And it will refresh to bring those rows back in from the original CSV file. Now when we close and load, you'll see in our query pane that Kickstarter project query is refreshing itself. And what we should see is that more data comes in here. Instead of just 41,000, this should show a higher total because we're now including projects with different project states. And that's exactly what we see. Now we see 127,875 rows loaded to this table. And just like you'd expect, we can close out our pane, head to our pivot, jump into Pivot Table Tools and refresh. And now check it out. When we look at our state filter, now we don't only have successful options, we have failed, canceled, live, and suspended as well. And there you have it. So very, very quick, very surface level demo of some of these basic Power Query tools. Again, if you want that deep foundational knowledge, check out the Power Query, Power Pivot, and DAX course. I think you'll really enjoy it. But hopefully for now, that at least inspired you to play around with some of these more advanced tools and see how they might be able to revolutionize your workflow in Excel. All right, for this pro tip, I'd like to introduce you to a very powerful concept in Excel. We're going to talk about how to build and analyze relational data models in Excel. Now, Excel's data model is used for a number of different purposes. For one, you can compress extremely large amounts of data, hundreds of millions of rows, if not more. Second, you can create table relationships, which is a much more efficient and elegant way to blend data across tables or sources without manually stitching them together with cell formulas. And third, you can add brand new calculated columns and measures using a formula language called DAX, or Data Analysis Expressions. So there are a few ways to get data into the data model. The most common way is to create a new connection to a data source using a tool like Power Query, also known as Get Data or Get and Transform, and load straight from that connection into the model. A simpler way to add data to the model, especially for the sake of demonstration, is to take a table from a worksheet, which is generally a much smaller table, and click the Add to Data Model button within the Power Pivot tab. Now, this is a good point to pause and let you know that some versions of Excel will not have access to these data modeling tools. So if you don't see your Power Pivot tab, the first place to check is File, Options, Add-ins, and look for your COM add-ins specifically. If you still don't see Power Pivot there, I'd recommend Googling where is Power Pivot, and you'll be taken to the Office Support website that looks like this. And here you'll actually see the exact Office products that do have access to these data modeling and Power Pivot tools. Now, assuming you do have access to the data model, once you've added your tables to the model, you'll be able to manage or edit your data model window and see a few different views like you see here. On the left, we have the diagram view, in which case we see our tables appear as individual objects, and that's where we can create the actual table relationships between them based on things called primary and foreign keys. On the right, we have our data view, which is a more traditional kind of tabular layout, but the beauty of the data model is that once these relationships are defined, once you've created what we call a relational data model, which for the purpose of this lecture, I'm defining as a group of related tables, then we can insert a pivot table to explore and analyze the data across all of these related sources in one single view. And that's why we call this a power pivot. It looks and feels exactly like a regular pivot table, but it's sitting on top of a data model. So common use cases here, combining information from multiple sources without actually mashing it together by merging or using functions like lookup or index. And two, this is the foundation for building robust business intelligence solutions that can integrate and blend data sources from all sorts of places like sales data, HR, finance, marketing, etc. So with that, let's jump into Excel. I'm going to run through an extremely quick, very brief demo to showcase some of what these data model and Power Pivot tools can do. All right, so if you're feeling brave and you'd like to follow along, head to your table of contents in your Pro Tip workbook. We're looking for the purple analytics tips here, and let's jump into the data modeling demo. It's a 4-star demo. We'll go ahead and link out to that sheet. And what we're looking at here is a table called transactions. We've got the transaction date, column A, we've got the product that was sold in column B, some information about the customer based on a customer ID here in column C, and then the actual values here, the quantity sold in column D. Now, on its own, this table isn't very helpful to us. We could plug this into a pivot table and we could roll up the quantity or the sales, for product IDs or customers or days. But what good does it really tell us that we sold product number 76 6 times, right? We have no additional context about these IDs. So what we'd really like here are some lookup tables that could potentially map this product ID or this customer ID to additional dimensions or additional pieces of information that we can use to really learn more about these sales. And in fact, that's exactly what we have if we expand these grouped columns. You'll see we have 3 more tables. We've got a green table called products. We have an orange table called customers and a yellow table called calendar. Now, as you might expect, each of these tables includes an ID column, or in the calendar case, a date column, which can map this information back to our transactions data in columns A through D. In other words, if we know the product ID, which we do, then by creating a connection or relationship to the product table, then we also know the product brand and the product name, as well as the retail price and cost. Same goes with the customer ID. That key can be used to pull in information about those customers, the names, the cities, the countries, marital status, gender, what kind of membership they have. All of that information can be tied into this transaction table because we have the key columns that can connect them. So you might be tempted to go ahead and start writing functions like VLOOKUP or index match to tie these together into a single master table. Because in old school Excel, we're used to needing a single table or single source for our pivot tables. That was always the one big limitation of pivots. So maybe you'd type, a VLOOKUP here. We're looking up the product ID within our products table and grabbing the second column with an exact match. And boom, there we go. We have our product brand now in column E. So we've tied that product brand in to our transaction table. Now listen, we could continue this process to pull in product name, retail price, as well as all of the customer information and all of our calendar information as well. But there are 2 problems with that. Number 1, what if these tables included hundreds of columns instead of just a handful like we have here? All of a sudden, this approach isn't quite as scalable. And 2, what we've created is a really inefficient table with a ton of duplicate values that simply aren't necessary. So let's go ahead and delete that column here. And I'm going to show you the more elegant, the more sophisticated approach to accomplish the same thing using the data model. So I've already added these tables to the data model, but if you'd like to practice yourself, you would select an individual table, drill into your Power Pivot tab, and click this Add to Data Model button right here. Now, because I've already added them, we can go to our Manage button, which will open up the data model window. Here we're in our data view by default. We can see these 4 tables in tabular format as separate tabs, and diagram view, which actually shows each of our tables as an object on the canvas. Now you'll notice these lines connecting the tables represent relationships. So in this case, product ID, which is highlighted, is what connects products to transactions. We have our customer ID, which connects customers to transactions. And finally, we have our transaction date, which connects to the date field in our calendar table. Now, to show you how to create these relationships from scratch, I'm going to head to the Design tab here, Manage Relationships, and all we need to do is select these 3 relationships, press Delete. Okay. And when we close that dialog box, now we'll see those tables kind of disconnected again. And all we need to do, it's as simple as grabbing the field we want and connecting it to a primary key within the lookup table. So transaction date to date, product ID to product ID, customer ID to customer ID. And it's as simple as that. In a matter of under 10 seconds, we've replicated all of the effort of creating those lookup or index functions to manually stitch that data together, and we've accomplished the exact same result. And now here's the best part. If I head back into the Home tab here and insert a pivot table in a new worksheet, we'll press OK. Let's double click to name this tab something like Data Model Pivot. Here's the beauty of it. Now we're dealing with a power pivot, which is technically the same old pivot table layout, just sitting on top of a data model. And we have access to all of our data model tables, calendar, customers, products, and transactions, as well as other tables in the workbook, which in this case won't be helpful because there's no relationship defined between them. So if we drill into our transactions table, you'll see a few different measures here that I've defined, transactions, total quantity, and revenue. These were designed with a language called DAX, which is out of the scope of this course, but it's something that I do cover in my Power Query, Power Pivot, and DAX course. So let's grab total quantity, pull that into our values here, and now we can access any one of our other tables and break those quantities down in all different ways, like by product brand on rows, for instance. Here we can see that American product sold 1,200, Atomic product sold 695. We can grab a field from our customer table as well, like the customer city, drag that in as secondary row labels, pull product brand out. So as you can see, I'm manipulating this pivot exactly like I would manipulate any other pivot table in Excel. The only difference is that now I'm able to access fields across 4 different tables that are connected only with the relationships that we defined within the data model. Incredibly powerful stuff. All right, time to dive into a 5-star, truly expert level analytics tip. We're going to talk about how to explore data models outside of pivots using something called cube functions. Now, 2 quick caveats before we dive in. Number 1, if you haven't viewed the data modeling pro tip or you haven't learned about data models in the past, I'd highly encourage you to do so. Number 2, you're going to need a version of Excel that's compatible with the data model and with Power Pivot. If you're not sure, go on Google, search for where is Power Pivot, and you'll jump to the Office Support website that looks like this. And here you'll be able to see the exact versions of Excel that include access to these data model and Power Pivot tools. Now, let's get back to it. So, cube functions. The easiest way to explore data in a data model is through a pivot table or a Power Pivot. But what cube functions do is allow you to pull or retrieve specific filtered values out of your data model and pull them directly into worksheet cells. So for instance, if you want to create a view that looks like this, you can use cube functions to do this. And in my experience, there are 4 types of cube functions that I use almost exclusively. The first is called a cube set, and essentially a cube set is a collection of items or cube members from your model. It's essentially equivalent to an entire column from a table in your model. In this case, we've defined a cube set that contains information about product brands. Now, within cube sets, you have something called cube members, and these are shaded in blue here in the visual. A cube member is a single item from within a cube set. So in other words, it's one item out of a table column. Here we're looking at different values within the membership column in our customer table: golden, silver, bronze, and normal. And note that we also use cube members to define quantitative measures or calculated measures like transactions or quantity. Next up, we have a special type of member called a cube ranked member. These are shaded in green here in the visual. And these are just like cube members. They're individual items within a cube set. The only difference is that they're based on an ordered rank, and that's what allows us to do things like show the top 5 products by quantity, for instance, like you see here. And last but not least, we have our 4th primary type of cube, which is the cube value. And those are all of the cells shaded in yellow. They're the actual numerical values that we're aggregating based on a set of member expressions. And those member expressions help us filter down those values to retrieve the proper numbers. Now, these can definitely be tricky and a little unfamiliar to work with at first. I'm going to walk you through exactly how to build a view just like this, but keep in mind that there are many other types of cube functions as well, and I've included a link for more info here. What this short link will take you to is the Office Support documentation page for cube functions, which looks like this. And here you can scroll through and learn a little bit more about the fundamentals of cube functions and some of these other options that I'm not covering. So common use cases here: for one, building spreadsheet-based reports or dashboards that sit on top of data in your data model without having to rely on pivot tables. And 2, cube functions can be a great way to document all of the sets and members within your data model. So with that, let's jump into our pro tip workbook and practice building a report view like the one you see here. All right, so if you're following along with the course, you know the drill. Head to your table of contents, scroll to your purple analytics tips here. We're going to drill into this 5-star cube function demo. Go ahead and link out to that sheet. Now, what you're looking at here is a basic blank template that I've created of a sample report. There's no formulas or anything here, it's just formatted cells, and our goal is to convert this and wire it up into a fully functional report that pulls in data from the underlying data model. Now, to get started, we need to do a quick review of the data model that we're working with. So I'm going to jump into the Power Pivot tab, click on Manage the Data Model, and let's jump into Diagram View here. So this is the model that we're working with in this workbook. We've got transaction data with 3 calculated measures: transactions, total quantity, and revenue. Those are the measures or metrics that we're going to pull into our report. And we also have a number of fields that we can pull from these 3 lookup tables. We've got calendar fields like the day, the month, the quarter, and year. We've got customer information like countries and cities, gender and member card status, and products, which include things like the brand, the name, the retail price, and the cost. So let's go ahead and actually insert a pivot table from our data model, and I'm going to drop it into an existing workbook. I'm going to put it right here in our cube functions worksheet, and let's drop it right here in cell H2 and press OK. And what we'll do is use this pivot table to help spot check and QA and make sure that the numbers that we're populating with cube functions are accurate. And then once we've done so, we can go ahead and delete the pivot itself and be left with just the custom report that we've built. So as you can see here, we've got a few different breakouts of the data. We're looking at 3 different metrics: transactions, quantity, and revenue. First, we're breaking it down by month for the previous 3 months, April, May, and June. Then we're doing a breakdown by member type, gold and silver and bronze. And this third table here is showing the sales by product for the top 5 products based on either transactions, quantity, or revenue. So let's start at the top with sales by month. And I'm going to drill into this pivot, and I'm going to pull in some of these fields: transactions, quantity, and revenue. And in this case, we want to break it down by month from my calendar table. We grab month name, pull it into rows. And in this case, all we really care about are April, May, and June. Press OK. Let's sort it A to Z. So this is a little preview of the view that we're trying to achieve right here by pulling those same values into the worksheet cells themselves. So if you recall, the cube value function was the type of cube that can pull in or aggregate those numerical values. Problem is, if we start by just typing cube value, we're going to open the parenthesis. Our connection is going to start with an open quote, and it's going to be this workbook data model. You can press tab to lock that in, close the quote. Now, the second argument and the third and the fourth and the fifth for a cube value function basically ask you to point to a member expression. And that member expression helps tell Excel how to filter down the values to return. So in this case, we're filtering down based on 2 different conditions or criteria: the month name in B5 and comma to the measure name in cell C4. So that's really all I need for this cube value function. If I close the parenthesis, press enter, I get an NA. And the reason I get this error is because cube values don't know how to interpret cells that just contain text. So right now, this cell means nothing. It's just a string of text that says transactions. Same thing with my month names: April, May, June, gold and silver, bronze. So what we're going to need to do is convert these text strings into actual cube member functions. So let's start with our metrics here. We can type equals cube member, open quote, this workbook data model. We're going to start like this every time, comma over to the member expression, and this is the field or the item from our data model that we want to capture in this cell. So open another quote. This will allow you to access the tables and fields in your model. In this case, we want a field from our measures, and if we enter a period, it takes us to the next level in the hierarchy, which is the actual list of measure options here. And we want transactions. So I'm going to tab it in, close the quotation, close the parenthesis, press enter. So now it still says transactions, but now this is an actual cube member. And we're going to go through the same process here for April equals cube member from this workbook data model, and the member expression, remember, open the quote again. This time it's coming from the calendar table, period to the list of columns, We want the month name column. And now because we want a specific month within the month name column, we're going to add one more period and type the name of the month surrounded in brackets. So we want specifically the month of April. And then close the quote, close the parenthesis. Feel free to pause on the screen for a moment to make sure that you've got the right function. And I'm going to press enter and check it out. Two things happen. Number one, my cube member cell now takes a value of April, which is not just text, it's an actual cube member. And our cube value is now returning a proper number, which is 6,588, which we can map to our pivot as a QA, and that does match. So we are on the right track. And now that we've defined some of these, it's very easy to apply them to the rest of our cells. So we can grab this transactions column, copy it, paste it 2 more times, and then simply adjust that last argument from transactions to total quantity, and from transactions to revenue. Press enter. Same thing with April, May, and June. I'm going to paste this 2 more times and just change the April in the final argument to May, and finally to June. And just like regular Excel functions, we can treat our reference types carefully here. Because our months always live in column B, we can fix that column reference. And because our headers, our measures, always live in row 4, we can fix that row reference and press enter. And check this out. Drag down, drag over, and boom, we've got all of our cube values populated. We can check against the pivot. All looks good. And now we're starting to cruise here. We can actually grab one of these cube members from month. We can paste it into the member type template here. And now instead of the calendar table, we're going to open this up, and we want a field from our customer table. And the column that we want is the member card column. And in this case, for the first value, the member specifically that we want is golden. So we can type it in, close the quote, close the parenthesis, press enter, and then copy that 2 more times to populate silver and bronze. So silver right there, and bronze right here. And now check it out. Copy this cube value, paste it down. Only the references that we want to move are moving. The other ones are fixed. They're still pointing to the correct headers up here, as well as the proper members for member type here in column B. So let's go ahead in our pivot. Let's pull month name out, pull member card in, and we can just kind of resort this a bit. Gold at the top, then silver, then bronze. These are the values we should be seeing, and boom, those are the values that we do see right here from our cube values. So we are 2 for 2. The last thing that we need to do here is populate this sales by product matrix, which is going to pull in the top 5 products. So here's the catch. We don't know offhand what the top 5 products are. So we can't just start typing regular cube members from scratch like we did with month or member type. Now we could sort the different product brands in the pivot to figure out what the top 5 will be, but if we want this view to change dynamically and always sort based on current data, we've got a better approach to do that. And what we're going to do here is introduce a cube set first here in column B16. So let's go ahead and type a cube set function this time. As always, going to start with the connection to this workbook data model. And now the set expression is going to be the list or the collection of product brands, which are going to come from our product table. So open the quote, products dot product brand. And now here's the key, the last little option after the dot. I don't want to select all, and I don't want to select any specific item. So I'm going to type members, which is going to force this cube set to store all of the possible members within that product brand column. Close the quote. And now we need to update or populate the additional arguments here. So for the caption, what we want the cell to display, let's do brands. And now the sort order, this is how we determine how any cube ranked members get sorted within this set. So in this case, we're going to sort descending, high volumes on top. So that's number 2. And what do we want to sort by? Well, we can choose any one of these measures. Let's go ahead and choose transactions. And because that comes from our measures table, I'm going to open the quote, measures dot transactions, close the quote, close the parenthesis, pause the screen for a moment, make sure you've got that down. It's a long function, and we'll enter that in. So all we see is the word brands here, but this cell contains an entire set of members, and that's going to allow us to now use something called a cube ranked member to pull individual items out of that set. So check it out, equals cube ranked member from this workbook data model. Now the set expression is a reference to a cube set, which we just created here in cell B16. Let's press F4 to lock it in because that cube set will always live there. And now for rank, you'll notice that I've created a little index from 1 to 5 there in column A. That's going to be our rank index. So let's just point over to that rank number, and we can go ahead and close off the function, press enter. And the first item we see is all. If we click and drag down, we see a few different product brands appearing: Hermanos, Telltale, Ebony, and High Top. Now the issue is that all is not an individual brand. It's actually the total across all brands. And that will always show up at the top of a cube set. So the easiest way to adjust for that is to simply start with rank 2, then 3, then 4, then 5, then 6. And because we've set our references well, copy that value, paste it down, drag it down, drag it over. And it's looking good, but let's do one final QA in our pivot. We're going to pull member card out, drill into products, pull product brand in, and we're going to sort those product brands descending by transactions and press OK. Check it out. Hermanos, Telltale, Ebony, High Top, Tri-State. Same exact 5 that we populated using cube ranked members and cube sets, and it looks like the transactions, quantity, and revenue values match up perfectly. So the pivot has done its job. I'd recommend keeping one just for quick and easy data exploration. But in this case, we can go ahead and select those columns, delete the pivot, and there we go. We're left with our perfect custom formatted report that we built entirely using cube formulas. All right, I want to share one of my favorite advanced analytics techniques in Excel. This is a 5-star expert level tip. What we're going to do is build our own Monte Carlo simulation model entirely within Excel. No VBA, no macros, just straight up cell formulas and data tables. Now, Monte Carlo simulation, it's typically used to predict the probability of some future outcome or outcomes based on repeated random sampling. In other words, we randomly simulate the same outcome over and over and over and over again, and then analyze the resulting array of results. So what better way to demonstrate Monte Carlo simulation than to build our own roulette simulator in Excel? So the way this works is that you can place a certain type of bet, red or black, even or odd, specific numbers, and each bet is associated with a given payout. So after placing your bet, determining a wager, we're using ran between to essentially randomize or simulate a spin of the roulette wheel. In this particular case, we've bet $10 on red. The result is the red number 23, so we won $10. But the goal isn't just to sit here and randomly spin over and over and over again. What we want to create is something like this, where we're actually recording the results of a number of simulations, in this case 10 spins, and then evaluating those results and summarizing them with basic stats functions. So here we're calculating the total gain or loss, the number of spins, the number of wins versus losses, the win percentage, average return per spin, and basic max and min. And the tool that we're using to actually drive these simulations is Excel's data table. So we're going to head to our data tab, drop into our what if analysis tools, and use the data table to create and record as many simulations as we determine. Now, obviously we're using this to kind of create something fun and interesting, but there are a number of very serious, very realistic use cases where this could come into play. For one, randomly simulating a business model thousands of times in order to understand the probability of something like a profit versus a loss. Or to build on that, creating predictive models that actually can account for a given degree of uncertainty for one or more model inputs, like what interest rates will do in the future or how supply costs will change. So this is an incredibly powerful data science and analytics tool that we can play with and learn about right here in the familiar Excel environment. So let's go ahead and jump into our pro tip workbook and practice building some of these simulations. Alright, so if you'd like to follow along, head to your table of contents, scroll on over to the analytics tips here in purple, and we're going to jump into our Monte Carlo simulation demo. Go ahead and link straight out to that tab, and here we'll find our roulette simulator. Now, for those of you who aren't familiar with the game of roulette, this is what the table looks like. You've got 36 numbers, half black, half red, as well as 2 green numbers, 0 and 00. So the dealer will spin a wheel that contains all 38 slots associated with each of those numbers. Now, as far as bets are concerned, you can place bets in a number of different ways, which you can see here in this drop-down cell. You can bet on individual numbers, which are the most uncommon results, and therefore pay out the highest, in this case $35 to 1 on your bet. You can also bet on the first third of numbers, the first 12, second 12 or third 12, the first, second, or third column of numbers, the first half, second half, even numbers, odd numbers, red or black. So as a simple example, let's say we bet on black. We can input a certain bet amount, let's say $10. This payout tells us that a bet on black pays out 1 to 1. So if we win, we get $10. If we lose the $10 that we wagered. So from here, we can press the F9 calculate button or head to our formula tab and click the calculate now button to simulate different spins of the wheel. So as you can see, we've bet on black. So any red result means that we lose our bet, down $10. Any black result means that we win $10 because of the 1 to 1 payout. Now what we really care about is the information down here, our simulation data and our simulation results. So right here, this is where we're going to use a data table to actually spin the wheel 10 times virtually and record the results of each spin here in column C. And I've already populated some functions in column F to summarize those results. I've created a named range called spins, and we're using a basic sum to calculate total gain loss. We're taking the max of column B for the number of spins, using COUNTIF to calculate the wins, and so on and so forth. So let's go ahead and start with a small number of simulations, just 10 spins. So what we're going to do here is select this entire range from B15 through C25. And remember that when we use data tables, one of the cells in the selection needs to contain the formula that we're simulating, which in this case is the spin result housed in cell I9. So I've simply referenced that result right here in C15 so that we can select the entire reference as we insert our data table. So head to your data tab here. We're going to go to the what if analysis options, click data table at the bottom, and here we've got our 2 criteria, our row input and our column input. Now we don't have any variable values that we're testing in rows, so that's obviously going to be blank. But here's where things get a little bit strange. We do have different values here in our column, so we need some sort of a column input, but these values don't actually feed into any input that impacts our result. In other words, we're not actually plugging the number 1 or 2 or 3 into some formula input. We just want to randomize that formula a certain number of times. And to make Excel realize that, all we have to do is reference a blank cell. So cell B14 is completely blank. We can use that for a column input and press OK. And there you go. Once we've done that, Excel is now iterating through this data table. You can see it's created a single array containing all of the results, and it's recorded a series of results, wins and losses, in this case based on 10 different spins of the wheel. So in this first example, we're betting a $10 wager on black. We spun it 10 times. We ended up winning $40 because we hit black 7 times. We hit red or green, meaning we lost, 3 times. So our win probability was 70%, and our average return per spin was $4. So let's go ahead and try another simulation by just simply calculating now. Okay, this time we lost 20. Win percentage was only 40%. Again, now we lost 60. We only won twice out of 10 spins. Spin again, lost 60, lost 40, Broke even that time, lost 20. So as you can see, there's quite a bit of variability in terms of that win probability. Now, we know the actual stats here. We know the real probabilities. The odds of winning a red or black placement in roulette are equal to 18 winning results out of 38 possible results, which equals 47.4%. And the reason this win probability that we see here in cell F19 is bouncing around so wildly and not even really targeting in on that true probability is that we're dealing with a very, very small sample size. Anything can happen in 10 spins. You could win 10 out of 10, you could lose 10 out of 10. So what I'd like to do here is repeat the process, not for 10 spins, but for 10,000 spins and see what happens. Now keep in mind, you can't just delete an individual cell from your data table, which is an array. You have to select the whole thing, starting with C16. I'm going to Control Shift arrow down and then delete. And I'm also going to delete these spin index numbers here. And little pro tip here, I'm going to select the number 1, hover over the right corner of the cell, hold the right click on my mouse as I drag down and back up. And when I release, I'll get this secret menu here that has a series option at the bottom. And what I want to do is fill a series in this column. I want to step in integers of 1, and I want to stop at 10,000. So press OK. And there we go. If I control arrow down, you'll see it's created a series all the way down to 10,000 spins. Now, same process as before. I'm going to select this range, Control Shift arrow down to grab the entire range of cells, data, what if analysis, data table, no row input, column input equals blank cell B14, and press OK. And now it's going to think for a little while because it's iterating 10,000 times and recording the result. And let's see what happens. There we go. So we're making the same bet as before. We're betting $10 on black. The only difference is instead of making that bet 10 times, we just made that bet 10,000 times. It was a very long night at the casino. And the result that we see here is a total loss of $4,980. You can see we spun it 10,000 times. We won 4,751 times. And take a look at that win probability. Remember what we said the actual true probability for this bet is? 47.4%. Here we see a result of 47.5. And if we go ahead and spin it one more time by hitting calculate now, remember it's going to take a few seconds, usually 10 seconds or so, to actually run through the simulation. And there you have it. So 47.6. This time we lost $4,900. And let's just do one more calculation. Give it a few seconds to run. There we go. Our third result, we only lost 3,400 that time. We had a higher than normal win probability, but still very, very close to the true percentage or true odds of winning. So what I'm actually going to do here is select that entire range here and delete that data table just because I don't want to slow things down here. And let's go ahead and just delete these index values down to 10,000, and we're kind of back where we started. So from here, feel free to play around, try different types of bets, try different bet amounts, simulate different numbers of spins. It's totally up to you from here. But that's your basic crash course in creating a Monte Carlo simulation model in Excel. All right, I am so excited to share this next pro tip with you. This is a 5-star, truly expert level analytics tip. We're going to talk about optimizing complex models using Solver. Now, what Solver is designed to do is work with real-world complex optimization problems that require multiple inputs or decision variables subject to a given set of constraints. Now, consider a case like this. Here we're looking at a transportation matrix that tells us the cost to ship goods between 4 different factories, Boston, New York, Chicago, and Oakland, and 4 different distribution centers, Miami, Dallas, Seattle, and Baltimore. And we're going to be walking through this in depth when we jump into Excel, but the bottom line, the objective here, is to figure out how many units of product to ship from each factory to each distribution center in order to minimize our total shipping cost. Now, it's not quite that simple because in the real world we have constraints and limitations as well. For one, we need to fulfill all of the orders demanded, in this case 6,000 total orders, and two, we can't exceed the inventory available at each specific factory. So for a problem like this, we really can't use simpler tools like goal-seek, which required a single input or decision variable and a single concrete outcome. In this case, we need to use solver, because solver allows us to either minimize, maximize, or target an objective value. It allows us to change multiple input cells or decision variables, and it allows us to determine specific constraints as well. So what we're going to do here is head to our Data tab and click on the Solver button to launch the Solver Parameters box. Now, if you don't see Solver in your Data tab, keep in mind that most versions of Excel have Solver as a built-in plugin, but by default it's typically not enabled, so you may need to head to File, Options, Add-ins, and then drill into your Excel add-ins to plug that in. Now, looking at this dialog box here, there are three parameters that we'll need to determine. Number one is our objective. In this case, our objective lives in cell E23. It's our shipping cost, and our goal is not to set that shipping cost to any specific value, it's to minimize. Number two, we determine exactly which variable cells or input variables to change in order to meet our objective. So here our decision variables live in cells D16 through G19. And last but not least, we need to optimize subject to a specific set of constraints. So in this case, we can't ship fractions of units, so our units need to be whole numbers or integers. We can't exceed the inventory available at each factory, and we need each distribution center to fulfill its entire demand. Now, one very quick note about solving methods, which you'll see right beneath that constraint window. There are three different options you can choose here. I'm not going to go into the details, it's well outside the scope of this course, but rule of thumb, you're going to use simplex LP for any simple linear optimizations like the problem we're dealing with here, and GRG or evolutionary for more complex nonlinear optimizations. The big difference between those two is that GRG is much faster but may not provide the global optimal solution. Evolutionary is more likely to provide that global solution but takes a lot longer to calculate. So now that we've set our objective, our decision variables, and our constraints, we can go ahead and click Solve and check it out. Excel will produce or populate all of the values in those decision variables to minimize our bottom line shipping cost. So here we see that we're shipping 225 units from Boston to Miami. We're shipping 975 from New York City to Dallas, 500 from Oakland to Seattle. And at the end of the day, we're meeting the demand. We're shipping all 6,000 units. We're not exceeding our inventory at each factory. And our total shipping cost comes in at just under $97,000. So as you can see, incredibly powerful tool. Common use cases, just like we see here, determining optimal results subject to real-world constraints. Things like limited inventory, like price floors, like integer values, etc. So with that, let's jump into our pro tip workbook and solve this optimization problem step by step. All right, so if you're following along, head to your table of contents, scroll all the way over to your analytics tips, and we're going to link out to our solver demo here. And here you'll see that transportation matrix that we talked about in the slide. But before I dive in, pop into your Data tab and look for that Solver button. It's usually all the way on the right. If you don't see it, head to File, Options, Add-ins, and then from this drop-down, you're going to want to manage your Excel add-ins and press Go. And you should see Solver add-in in this window here. Just pop a check mark in that box, press OK, and you should see that pop up in your Data tab. Now, returning to our problem here, what we have are transportation costs, the actual cost to ship a single unit from our factories to our distribution centers. And this is based on actual mileage, right? So shipping from Boston to Baltimore is quite cheap, only about $4 per unit, but shipping from Boston to Seattle is much, much more expensive, over $30 per unit. Now we're also dealing with two different constraints here. We have supply constraints, which is the limit to the number of units that each factory can supply. So Boston currently only has 1,000 units in stock. New York City has 2,000, Chicago has 2,500, Oakland only has 500. So we can't ship more units than a given factory has in inventory. So that's constraint number one, or supply constraint. We also have demand constraints, which are listed right here in row 10, which says that, okay, Miami only needs to fulfill 1,250 orders. So it doesn't make sense to ship more units to Miami. And in fact, we can't ship fewer units to Miami because we need to fulfill these orders. We need to get these products into the hands of the customers who ordered them. So we've got to get 975 to Dallas. We've got to get 3,250 to customers in the Seattle area, and so on and so forth. So those are our demand constraints. And bottom line is that there's 6,000 units that we're looking to ship here as part of this model. Now, if we jump down beneath the transportation matrix, we have our objective, or our outcomes. So the goal here, again, is to populate these values right here in D16 through G19. Those are the input or decision variables that will be changed in order to evaluate or calculate the total shipping cost. So watch what happens if we just plug some numbers in. Let's say we ship 100 units from Boston to Miami, 50 from New York to Dallas, 350 from Chicago to Seattle, and 25 from Oakland to Baltimore. As you can see, we're calculating the number of units shipped per factory. We're going to make sure that those numbers don't exceed these constraints in I5 through I8. We're also calculating the number of units received by each distribution center, and we'll want to make sure that these numbers don't exceed or come in under the ones here in D10 through G10. These have to be exactly equal at the end of the day because we've got to fulfill those orders. And then last but not least, our total shipping cost cell, this is our bottom line objective that we care about, is a simple sum product function that basically takes all the units sold or shipped from each factory to distribution center, multiplies them by their respective costs, and then sums up the total to spit out that total shipping cost. In this case, for the 525 units that we just plugged in as a demo, that would cost a little over $10,000 to ship. So we know our objective, we know our decision variables, and we know our constraints. It's time to solve this thing. So let's go ahead to Data, click on Solver, and here you'll see your solver parameters. So first things first, what's our objective? Well, our objective is shipping cost, which lives right here in cell E23. And we don't want to set that shipping cost to any particular value, although we could if we wanted to. And we certainly don't want to maximize the cost of shipping. That would just be crazy. We want to minimize our shipping cost. And we're going to do so by changing a certain set of variable cells or decision variables, which live right here in green, D16 through G19. There we go. And the only thing we need to do now is set our constraints. And there are going to be a few different constraints. Let's go ahead and add the first. Now our first constraint, which is a simple one, but it's important to add in here, is that we can't ship fractions of products, right? We have to ship whole units or quantities. So we know that our decision variables here, D16 through G19, have to be int, which indicates that it must be an integer. So press OK. There we go. That's constraint number one. We're going to add two more. The first is going to be our supply constraint, which means that our units shipped out, which live here in I16 to I19, units by factory, have to be less than or equal to the number of units that each factory has available. And note that I can do this in one step by selecting kind of the entire array of 4 cells. The alternative would be to turn this into 4 different constraints, where I16 is less than or equal to I5, I17 is less than or equal to I6, but we can do it in one step by selecting all 4 cells at once. So again, this says that we can't ship more units than a factory has. Press OK. And then our third constraint is our demand constraint. So we've got to fulfill the entire demand for each distribution center. So the units received by those distribution centers lives right here in D21 through G21. And in this case, we can't be over or under. We have to be exactly equal to the number of orders demanded or units demanded for each of those locations, which live right here in cells D10 through G10. Press OK, and we are good to go. Solving method is going to be the simplex LP option since this is a linear optimization case. And check it out. All we need to do now is click solve. And almost instantly, we get this results box that says solver found a solution. All constraints and optimality conditions are satisfied. And note that it plugged in the values right here in our decision variables, and it spit out that minimum total shipping cost, which in this case is $96,687.75. So let's go ahead and keep that solver solution. Note that we can save these values as a scenario in our scenario manager, or we can just press OK. And there you have it. We have optimized this very complex logistical challenge by determining exactly how many units to ship from 4 different factories to our 4 different distribution centers. And there you have it. Quick demo of how to use Excel's solver tool to solve these types of more complex real-world optimization problems. All right, this next pro tip is a little bit of a teaser, kind of a sneak preview into some different ways that you can explore your data using something called the Analysis Tool Pack. So just like Solver, the Analysis Tool Pack is a built-in Excel plugin that's designed to support a range of more advanced and complex data science and statistical tools and methods. Things like analysis of variance, ANOVA, covariance, regression, t-tests, histograms, and so on. Now, obviously, I don't have time to dive into each of those specific methods in turn. They each deserve a much deeper, much more comprehensive review. But what I will show you is the scope of options available within this tool pack, as well as a few that we can use right off the bat that are simpler but no less powerful. So in this demo, we're going to be looking at a sample of about 5,000 Olympic athletes, along with their ages, heights, and weights. And what we can do is drill into our Data tab and look for the Data Analysis button. If you don't see this, it likely means you just need to activate that add-in. So go ahead to File, Options, Add-ins, and manage your Excel add-ins to activate this tool on your ribbon. And once you click through Data Analysis, you'll see a scrolling list of all of your different options here, some of which are simple, some are quite advanced. Now, for the sake of demonstration, we're going to be talking about 2 options here. First, we're going to look at a correlation matrix between our 3 fields, age, height, and weight. And then from there, we're going to generate some descriptive statistics to calculate things like the mean, mode, variance, range, the count, skewness, min and max values, and so on, without having to type a single formula. So that will be a great way to really describe and understand our data with the click of a button. So common use cases here, just like I showed you, generating those descriptive stats without having to use formulas, and 2, exploring or analyzing data using these more advanced data science or statistical methods, like analyzing variance, building predictive models, etc. So let's jump into Excel and take this analysis tool pack for a test drive. All right, so go ahead and open up your pro tip workbook, scroll in the table of contents to your purple analytics tips, and we're going to jump into the analysis tool pack preview demo here. And when we link out, we'll see our list of Olympic athletes. Again, we've got a sample of about 5,000 athletes here. We're looking at ages, heights in centimeters, and weights in kilograms. So this will be a nice data set to practice some of these analysis tool pack options. So first things first, head to your Data tab. Off on the right, this is where you should see your activated plugins. If you don't see Data Analysis, go ahead to File, Options, Add-ins. You're going to manage your Excel add-ins. Press Go. You should see Analysis Tool Pack in that list. Go ahead and check the box and press OK. That should pop up right here. And let's go ahead and see what we have available to us. So as we scroll through, we'll see a number of different options here. Analysis of variance, correlation, covariance, exponential smoothing, moving average, random numbers, t-tests, z-tests, and a few others. So obviously kind of a range of level of difficulty and complexity here. some simple tools, some that are quite advanced. In this case, we're going to stick to a few basic options that you can utilize right off the bat, starting with descriptive statistics. So let's go ahead and press OK. Here we'll see a pretty intuitive dialog box. It says, all right, what's your input range of values? Well, I'd like to explore or analyze all three of these columns. So let's select B through D. These are organized in columns, so that's good. We do have headers or labels in our first row. And where do we want to drop this output? Well, let's put the upper left corner right here in cell F1. And let's also include the kth largest and smallest one value, basically a fancy way of saying the max and the min. And I think that should just about do it. We don't need to worry about confidence level for mean at this point. 95% default is just fine. Let's go ahead and press OK. And look at this. It's going to drop in all of these summary stats right here in columns F through K, literally in a matter of seconds. Now think about how long that would have taken to produce all of these values with cell formulas. These means, these medians, the standard deviation and variance would have taken quite some time, and we were able to just produce all of those values plus quite a few more in a matter of seconds. So looking at our max and min, looks like we have an athlete who is 65 years old, who's the oldest. Our youngest athlete was only 12. In terms of height, tallest athlete, 216 centimeters. And for those of you who aren't on the metric system, that's about 7 feet 1 inch. And we can confirm by simply filtering our source data here. Let's sort descending by height. And here we see Andreas Gliniadakis, who is a Greek national basketball player, which shouldn't come as too much of a surprise given how tall he is. And then looking at weights, looks like our largest athlete was 160 kilograms. Our smallest was only 35 kilograms. And same story here. Let's sort those weights ascending. And you can see that it's Aiko Sugihara, who's a Japanese gymnast. And again, for those non-metric folks, 35 kilograms is a hair over 77 pounds. So those are our descriptive stats, really, really helpful, but also quite simple to produce. Let's go ahead and do one more example here. Back into our data analysis options. This time I want to look at correlations or relationships between these three columns. So same input range here, B through D. Okay, they are columns again. We've got labels, headers in our first row. And this time let's drop our correlation output beneath our stats right here in F20. And it's as simple as that. Okay. And there we go. Let's go ahead and format these so it's a bit more readable as percentages. And check this out. We've got this correlation matrix that's produced here. You'll see 100% kind of on the diagonal because each field is 100% correlated with itself. But the ones that we really care about here are these two values as well as this one here. So I'm just going to make those bold. And basically what this tells us is that there's not much of a correlation or relationship between ages and heights, only about an 11% correlation, which might seem a little bit surprising at first until you realize that we're not looking at the entire population. We're not looking at heights all the way down to newborns or infants. These are all, well, for the most part, adult athletes. So once you've reached adulthood, you're not really growing anymore, so it's not surprising that we see a relatively low correlation there. And that same story holds for age and weight for the same reasons. Now what's interesting is that we do see a very clear, very strong correlation, 78%, between height and weight, which also makes sense because taller, larger athletes tend to weigh more. So there you go. That's a very quick way to use tools like correlation and descriptive stats to explore and learn more about your data set without having to use any fancy tools or formulas. And again, I won't be diving into the other kind of more complex tools within that analysis tool pack, but I'd encourage you to explore those options and try playing with those tools for yourself. So there you have it, quick primer, quick preview of the analysis tool pack.